So in the last lesson, we talked about the law of large numbers, and that is one of the two famous and important theorems about what happens to the sample mean, to that statistic we calculate from our observed data, what happens to it as the amount of data gets bigger and bigger. So what happens to the sample mean as n, our number of observations, goes to infinity. The other big important theorem about that is the central limit theorem. And so what it tells us in just sort of ordinary language is as n goes to infinity, okay, so as we're just getting more and more and more data, the distribution of the sample mean, distribution of that statistic, and again, the really important thing about that statistic is it's just based on numbers that we observe, the distribution of it becomes normal. Okay, so it's kind of one more piece of news that we have about the sample mean. In the last lessons, we learned that the sample mean's expected value is the mean of the population from which the observations are drawn. Okay, so the sample is a set of IID, random variables, so they're all independent draws from the same distribution. And in the last lesson, we learned that the expected value of the sample mean is the same as the expected value of that underlying distribution. Okay, we also came up with a formula for the variance of the sample mean. So if we have the variance, we also have the standard deviation, and that standard deviation of the sample mean gets called the standard error. I will probably start using that phrase. The final thing that the central limit theorem gives us is, okay, we know the mean, we know the variance of the sample mean, we actually also know the PDF as n gets larger. Okay, I don't want to oversell it. We don't know in small samples that that this statistic will have a normal distribution, but as we get more and more data, that statistic that we calculate is going to take a normal distribution. Okay, so the probabilities that that statistic falls in a particular place is going to have that normal distribution. And it doesn't matter what kind of distribution the actual data have. The data can have any kind of crazy distribution you want. The average of those data, the sample mean, as it's getting more and more data incorporated into it as n goes to infinity, the distribution of that, of the average value, is going to have a normal shape. Okay? And this is really, you kind of want one basic reason why the normal distribution is so important and so famous. It is because of that. It is because as we get more and more data, the average of the things we're observing will follow the normal distribution. All right. So that really is pretty cool, and we're going to really be admiring that fact throughout this last set of lessons here. I've just written in words what the central limit says. I think I want to write it the way you're going to see it in Ritsakis and Sissiklis and other math books. It tends to get written in kind of an unfriendly way, and I'm honestly not sure why people do that. But let's just write it the math book way here. Okay, so I'm going to write the central limit theorem to say let x1, that's a 1, x2, all the way up to xn, be IID, so independent and identically distributed. So they're all independent draws from the same distribution there. So the set of them is what we call a random sample. Random sample means IID. And they have, since they're identically distributed, they have the same mean. Let's call that mean mu. And they have the same variance too. Let's call that sigma squared. And let's remind ourselves what mn is, what the sample mean is. We just take those x's, x1, x2, all the way up to xn, we add them up and we divide by n. Okay. Given all that, then the limit as n goes to infinity. So the thing we're taking the limit of, I'm putting in square brackets here. What we're taking the limit of is a probability that a is less than mn minus mu over sigma divided by root n less than b equals 1 over 2 pi integral from a to b of e to the negative x2 times dx. Okay, that's what I meant. It's like not the most accessible way of writing this thing, but let's just unpack what we've got here. What we have over here on the right side, that is the standard normal, the integral of the standard normal PDF from a to b. Okay, so remembering that we like to use z to represent standard normal, this is just the probability that any standard normal is between a and b, okay, between these limits of integration. So it's the area under a standard normal curve from a to b. We know it's standard normal because we've got this kind of simplified version of the normal PDF that normally it would be x minus mu squared up here, but when mu is 0, that term becomes simpler, and we'd have a couple of sigmas floating around in it too, but when sigma is 1, it just gets simpler. So over here, what we just have is standard normal probability. And I do want to emphasize here, when I'm saying standard, it's not just loose talk. I mean it in the technical sense. Standard means it has a mean of 0 and standard deviation of 1. And that is what's over here. Okay. And what is the thing whose limit we're taking as n goes to infinity of? Okay. What is this here? This is the sample mean minus its expected value. Okay, so let's annotate this a little bit. So this is the expected value of the sample mean. And this is the square root of the variance of the sample mean. Okay, remember, we found that the variance of the sample mean was the population variance divided by n. So to get the standard deviation, we're just taking the square root there. So the whole thing in the center of this inequality in between the a and the b here, this is a standardized sample mean. Something that we've done several times this quarter. We've taken a random variable, we've subtracted off its expected value, and we've divided by the standard deviation so that it ends up with the transformed version here. Transformed version of the sample mean has a mean of 0 and a standard deviation of 1. Okay, and all this is saying here is that you standardize the sample mean, and the probability that is between a and b is the area under the standard normal curve from a to b. So that is the technically complete math book way of writing this basic fact that sample mean statistics distribution, the PDF that we can use to calculate its probabilities. And that is the cool thing about it, that PDF approaches a normal curve as we get more and more data here. And it actually, we're not going to do a simulation in this class, but if you do a simulation of it, it doesn't take that many observations for the sample mean to start looking pretty normal there. All right, so the additional thing that we're getting from the central limit theorem, just emphasizing, is we're getting the ability to calculate the probabilities that this sample mean falls in a certain range there. And that's going to turn out to be super empowering. That's going to let us calculate confidence intervals and do classical hypothesis testing. So that is where we are going in the next video.